can you see the slide, first of all, this principle for lead compensator design?
Yes, ma'am.
Just tell me whether you can see the slide. Okay, right. So before I start with this, let me tell you something. That is, I have sent you the remaining portion of the notes to both the sections by email, of which, as I had mentioned in the previous class, we will be, since this will be the last class today, I will try to finish off. Now, there would be, you will see that in that there are a few components which are, there. That is just for your reading. Reading means that you will it's mostly, as far as exams are concerned, it would be descriptive in nature and theoretical. So, I mean, in online exams, it's really not very relevant as such. But you would need to sort of know that such components do exist, what they do, and all that. So, I would request you to actually go through those, and if you need some explanation of some sort, you can just email me so that I can take a class in between, meaning that without going into the scheduled classes, because I believe your theoreticals are going to end by the end of this week, right? So, there wouldn't be any scheduled class after this. But in case you require any help for that portion means there are quite a few components over there. You would have seen if you just go through the notes. And those are the ones that I'm referring to. Regarding the compensator design, of course, we'll have a class today, and uh, you, I would try to sort of um, give you a satisfactory sort of exposure to the compensator design so that you are able to do the design, because unless there's a class taken for the compensator design, it's not going to be very easy for you to actually appreciate that. So I would like to dedicate the class to the compensator design rather than the control system components, as I told you, which are descriptive in nature, right? So you would require to go through that, but as far as your online exams are concerned, you can just leave it out that way. But naturally, sort of going through it will help you in the long run, right? So with that, now let me start with the principle for lead compensator design. Now, you would recollect that in the last class, I had discussed about a lead compensator and a lag compensator. And we had actually sort of seen how to, I would not use the word design, but how to find out the parameters of the compensator, respective compensator. If you decide on how much of lead you want, how much of phase that is lead you want, how much of magnitude contribution you want from the compensator, and at what frequency you want your compensator to be placed. Similarly, for the lag compensator, how much of lag you want and how much of magnitude attenuation you want from your compensator. If you decide on those are, known in definite terms, and from there you can find out the parameters of the compensator. I'll just, sort of quickly show you the slides, not describe, of course. So just to, yes. So we were doing this compensation using Bode plots, the lead compensator, and then basically some expressions were derived. This quadratic was of importance in the lead compensator, this one. And then we had said that, yes, alpha can be found out from the solution of the quadratic, and the parameter a can be found out from this expression. So those are actually the only expressions that we would be requiring in order to find a lead compensator. Let me admit. Okay. So, and we had done a direct problem in which the amount of gain required from the compensator and the amount of phase lead from the compensator, as well as the frequency at which the compensator is placed, all were specified. So from there, directly from the expressions, you can just solve and find out the value of alpha and a, and hence your compensator transfer function, right? So now today, actually, we are going to, similarly for a lag compensator. Just a moment. Okay. So similarly for a lag compensator, beta and b can be found out from the quadratic as well as this expression. And then basically, once you know the value that, sorry, once you know the amount of attenuation that you want from your compensator and the amount of phase lag you want from your compensator and the frequency at which you want to place your compensator, then you can just put those, I mean, values in your expression and then solve for it. So we had also done a numerical on that, and the compensator transfer function is directly obtained, right? So those were actually, I mean, the expressions used, or rather the expressions that would be used for designing have been derived. And once you decide on the values, meaning decide on how much of lead or lag you want from your compensator, how much of gain you want from your compensator, and at what frequency you want to place your compensator. If you decide on those values, basically you can directly find out the compensator transfer function. Unfortunately, I mean, as far as design is concerned, nobody is going to tell you that, oh, you put your compensator at such a frequency and this much of gain you would require from your compensator and this much of phase lead you would require from your compensator, etc. You would be, as a designer, you would be the person to decide on those values. So basically, if a practical problem is given to you would, first of all, the first step and the most, I mean, more important step rather, I would say, is to decide on the values that you require. If you, once you decide on the values that you require, you can directly put that in the expressions, and then you, I mean, mechanically you can find the compensator transfer function. So two steps involved, the first of which is decision, the second would be just finding on the basis of what you have decided earlier, right? So now I'm going to, I mean, today we are going to deal with principle for lead compensator design, meaning that here we are going to try to understand where to place our compensator, for what reason we are placing the compensator, that is, where to place it, and how much of gain and phase to ask for from the compensator. That would be done for lead compensator now, and similarly the lag compensator would be following. So this is specifically for the lead compensator. This one that I'm doing, lag, is going to be done after this. So now you need not actually read through that right now, but have a good look at the figure on the left side and the right side, right? There are two Bode plots that you see over here. Unfortunately, I cannot do board work. So, I mean, in case you do not understand what I'm trying to, I mean, show you by using the cursor only, please ask me to repeat or ask me to explain a bit more, because, I mean, without board work, it would be a bit sort of difficult to get across, in the sense that I hope you would understand. In case you don't, please ask me again so that I can repeat or explain a bit more, right? So now on the left hand side, there is a Bode plot, the magnitude and the phase plot. This is for a general system, any system. I mean, it's not for any specific system. It is for a general, I mean, physical system, right? So over here, the general trend that is shown is that basically the magnitude is shown as initially remaining constant and then, I mean, getting attenuated at a particular slope, right? So this is a general plot that we are showing just to explain things. Similarly, the phase is shown, phase plot is shown over here to be monotonically decreasing, right? Decreasing means going more and more negative, right? So this is a general plot that you see on the left hand side, right? The one on the right hand side, actually, one on the right hand side shows the plot, the Bode plot again, the magnitude and the phase Bode plot for a lead compensator. You would recollect that in the last class, we had actually seen that the plot magnitude, asymptotic magnitude plot would be like this, and the phase plot would be like this for a lead compensator. Now, with the help of this plot, we would try to, these plots rather, we would try to decide or try to understand how to decide where to place the compensator and for what reason, right? So now the first thing that we have to do is we would have to actually decide on a gain crossover frequency for the compensated system. Now, why decide on the gain crossover frequency for the compensated system? Because it is at the gain crossover frequency that we actually calculate the phase margin, right? So this you would be familiar with. In case you are not, let me just tell you in short, that is, the gain margin of a system is the amount of gain that is, I mean, additional gain rather, that is going to be required to make the system unstable. So we calculate the gain margin at the phase crossover frequency. Similarly, the phase margin is calculated at the gain crossover frequency. Now, for this particular design, whatever we are, I mean, the procedure that we are going to follow, we are going to assume that some phase margin is specified. So let us say that there is a system which is given to you, and it has been specified that your phase margin should be, say, 45 degrees or something, right? So now, I mean, from that point of view, we can decide on, I mean, uh, how to use a lead compensator on our system to get that amount of phase margin. So that is, I mean, the background. So for that now, we would have to first of all decide on a particular frequency where we want to place our gain crossover frequency for the compensated system. So what I'm trying to say is that this was, say, the original system. Original system means the uncompensated system frequency response is what you see on the left hand side plot, this one. It is the uncompensated system frequency response, the magnitude and the Bode, sorry, the phase plot of the Bode response, right? Now, when I place my compensator, where will I place the compensator, right? That is my question. So first of all, I decide on where I want to place my gain crossover frequency. So that is marked as desired gain crossover frequency. So let us say that after compensation, we want the compensated system to have the gain crossover frequency at omega 1, this one. Okay, so this is the desired gain crossover frequency. So if a phase margin is specified, where do I actually look for the phase margin? I will look for the phase margin at the gain crossover frequency. So at that particular frequency, I will now have to go to my phase plot and then see what is the, I mean, difference between this value and this is the minus 180 degree. I hope you can see it's written over there, minus 180 degrees. So the difference of the plot value, that is the phase of the system, and minus 180 degree, this amount is going to be the phase margin of the compensated system, right? If I place my gain crossover frequency over here. Now, one thing I have to keep in mind is that, okay, this is my desired gain crossover frequency. So I will place this right hand side as my compensator, lead compensator I am going to put, right? So first of all, how will I make my desired gain crossover frequency be over here? Naturally now, if this is my lead compensator magnitude plot, you can see that we had already earlier seen that the lead compensator magnitude value is either 0 dB or a positive dB, right? So now, if I have to place my lead compensator over here such that the desired gain crossover frequency is at a particular point, basically now I know that from my compensator, I will get a positive value of 0 dB, right? So I can place my desired gain crossover frequency in this range meaning, I hope you can see the cursor moving, right? This range, isn't it? Because, say, for example, if I place my desired gain crossover frequency from here to here, what is the existing value of the magnitude? It is already positive, right? So if I put my lead compensator anywhere within this range, I'm speaking only of the magnitude, it is going to be, this magnitude was already there plus a positive contribution from my lead compensator. So what will happen? The overall compensated system will have a magnitude which is this one plus the amount of magnitude that I get from my lead compensator, right? So that is not going to be, this plus something is not going to give me the gain crossover frequency, because at gain crossover frequency the magnitude would essentially have to be 0 decibels. That is the gain crossover. Crossover means where the 0 decibel occurs. Gain is 0 decibels, right? So the desired gain crossover frequency, if I mean using a lead compensator, cannot be placed within this range over here, right? What I have to do is I have to choose a range beyond the original GCF that was over here for my uncompensated system, and I can put the desired gain crossover frequency after that frequency. I can try to do the design such that my desired gain crossover frequency will be anywhere after that particular this after this value, right? So now let us see. If I place, say for example, the desired gain crossover frequency I want at omega 1. So at omega 1, originally the magnitude of the uncompensated system was, you can see, you can read that from here, it is going to be, um, this is in absolute scale, of course. Okay, this is an absolute scale and the other is in decibel scale. I hope you are familiar with the absolute scale, isn't it? Are you familiar with the absolute scale and decibel scale?
Yes, ma'am.
Okay. So absolute scale, you can see that this is an attenuation, right? So it's going to be a negative decibel. And from the compensator now, if I place it somehow such that I get some, I mean, additional value, say some M1 is the contribution that I want from my compensator, M1 decibels. So M1 decibels, if I place, say at omega 1, if I place the compensator such that this, I mean, value M1 is placed, and the compensator is I mean sort of, it's going to be placed like this such that I get that m1 value at my omega 1. So this minus m1 and the plus m1 is together going to make my magnitude value equal to 0 decibels ultimately. So I can try to use the compensator, lead compensator, in this range, that is beyond the gain crossover frequency of the uncompensated system. I can place it anywhere within this range from the point of view of the magnitude, right? Now, as far as the phase is concerned, okay, so somehow I have done that, meaning I've managed to, I mean, place my compensator over here such that I get that, I mean, to neutralize this minus m1 decibels, I use that plus m1 and, I mean, the compensated system gain crossover frequency comes to omega 1, right? So now let us see what happens to the phase. My desired phase margin was specified as some PM, the value, say 20, some, okay, 45 degrees or something. So that was PM, that is the phase margin which was specified. Now, if I put my lead compensator, the moment I put my lead compensator, I will get some amount of phase lead from my compensator. So if, I mean, I make the omega 1 coincide with this particular frequency because I want m1. So at this particular frequency, if the amount of phase lead is say phi 1, then what going to get the moment I put my compensator in my uncompensated system, what will happen is I will get a phi 1 phase lead from my compensator. So, in order to finally get PM as my value for phase margin, which is the desired value of phase margin, what I do is, first of all, I mean, that was the principle behind it. The First of all, what I do is I look at my phase plot, and then I try to see, okay, the phase plot at each frequency, I can calculate the difference with the minus 180 degrees. But naturally, I mean, the phase margin will be calculated at the gain crossover frequency, and that to the desired gain crossover frequency. So at the desired gain crossover frequency, finally, I want a phase margin of PM. So before the compensator is placed, I will have to look for the frequency where the phase margin is. Supposedly, phase margin is PM minus the phase phi 1. Why minus the phase phi 1? Because if I look at, let me just tell you in terms of numerical values, let us say that from the compensator, I'll get 20 degrees of lead. And my specified phase margin that I want from my compensated system is 45 degree. So now the uncompensated system plot is with me, right? So I will have to look for a place where in the uncompensated system, the value of supposedly the phase margin is 45 degree minus 20, yes, minus 20 degree. Why 45 degree minus 20 degree? Because now, I mean, that would make, okay, so I scan this and see, okay, here the value of the difference with minus 180 degree is 25 degrees. So now I choose this as my gain crossover frequency. Now, why did I do that? Because I know that, okay, I've now got from the uncompensated system, I've got 25 degrees already as my phase margin. The moment I put in my lead compensator, I'm going to get an additional 20 degrees, and that will make my phase margin requirement. It is going to make me meet my phase margin requirement, because after I put in the lead compensator at this particular frequency, the value of the margin will become the 25 degree plus 20 degree, which is 45 degree, which is the required phase margin, right? So for that, now what we would have to do is, I told you the other way around, meaning that, I mean, as if I already had decided on a GCF, naturally, that decision has to be taken on the basis of the phase plot, first of all, right? So, of course, the gain plot also. So let me just, with that background, let me go through the steps once more. That is, first of all, I have to get the Bode magnitude and Bode phase plot. So given a transfer function, I have to tabulate, I have to make a table of the phase versus frequency and the gain versus frequency, right? So now I will have to decide on whether I want a lead compensator or a lag compensator. Lag compensator we'll be doing. But let us say we have decided that, okay, we want to put in a lead compensator to get the desired phase margin, right? So if I want a lead compensator, then I will be knowing that, okay, the magnitude contribution from my compensator will either be 0 decibels or will be some positive decibels, right? So now I look at the magnitude plot. In the magnitude plot, wherever the magnitude was previously for the uncompensated system, it was already positive. I cannot put my desired gain crossover frequency, because in that range, if I put, I mean, if I want to make it make any frequency within that range, the gain crossover frequency, I will not be able to do that, because I'm going to add a positive value to a positive value. I cannot make it 0, make the magnitude 0, because at the gain crossover frequency, gain crossover has to occur, obviously, right? So 0 decibels is the value of gain that I would be wanting. So from that knowledge, I know that, okay, I would have to place my desired gain crossover frequency in that range. That is one thing that I would be understanding from my original, I mean, system, that is the uncompensated system magnitude plot. Now I can look at my uncompensated system phase plot, right? And there is a phase margin requirement which is going to be specified as per the problem. So if the phase margin requirement is specified, this method that we are studying is valid if the phase margin requirement is specified, right? So if the phase margin requirement is specified now, I would have to look at the phase plot and see how much the difference of the phase for the uncompensated system with the minus 180 degree is at each frequency. Of course, it's not, I mean, necessary to calculate at each frequency, but I would scan the plot and see now where the, supposedly, if I say that PM prime or PM dashed is the equal to PM minus 5, then PM dashed, I would have to look at where the value of PM dashed would be matching the PM minus phi 1. Why? Because from the lead compensator, I'll be getting a phase lead of some value, let us say phi 1. So if now I look at the phase plot and see that, okay, at a particular frequency, the amount of difference with the minus 180 degree is equal to the desired phase margin minus the lead I want from my compensator. So I will decide that this is the frequency where I would want my desired gain crossover frequency for the compensated system. So that now is the decision that I take on the basis of the phase plot. So where is it going to be? It is going to be at the desired gain crossover frequency minus the amount of lead that I would be wanting from my compensator. So that I would be actually, I mean, placing the desired gain crossover frequency over here. So once I do that, I decide on the gain crossover frequency. I say, okay, the gain crossover frequency is specifically, I want it at omega 1. So now, I mean, I would be able to say that the moment I put my lead compensator, the value, this plot, of course, both the plots are going to change. What will happen to the magnitude plot? Magnitude plot will become such that the compensated system gain crosses at the frequency omega 1. What will happen to the phase plot? The phase plot will, naturally, there is a lead that I will be getting from here. So the phase plot will actually be going above that. Above that means it's going to slightly shift upwards in frequency. And at the gain crossover frequency, basically the amount of phase margin will now become PM, because PM minus phi 1 plus the phi 1 that I would be getting from my compensator would ultimately make it equal to PM, that is phi, the phase margin that is specified, right? So now, if you look at this plot, that is the phase plot, if this side is, that is the difference with minus 180 degree is equal to PM minus phi 1, then what is the value of phase for that frequency? The value of phase for the system for that frequency is equal to minus 180 degree plus PM minus phi 1, right? So basically, I mean, this is the phase value. So this side I've put the phase value, whereas on this side, the other side, I've put the difference with the minus 180 degree, right? So basically, you would have to understand that. So basically, I mean, the phase value, if I look at the phase values, I would actually look at the plot, and then I would see where the value of the phase is equal to this value. This value means, say, I have already specified, okay, the 30 degree of phase margin is required and 10 degree of lead I want from my compensator. So if I do that, the phase that I would be looking for is minus 180 degree plus 30 minus 10. So that would give me, that value would give me this. That is, what should be the value of the phase that I'm looking for, and where I'm going to place my desired gain crossover frequency. What we would have to keep in mind when we are designing a lead compensator is that the phase, this second point that, okay, and first point, of course, I've already told you, let me read that out as well. So the for a lead compensator, the gain in dB at the desired crossover frequency should be negative. I mean, prior to the compensation, the uncompensated system should have a negative value of magnitude, because once I add the positive, then it's going to become 0, right? And the phase value must be minus 180 degree plus PM minus phi 1. So phase value means this much. That would be minus 180 degree plus PM minus phi 1, where PM is the specified phase margin and phi 1 is the amount of lead that I want from my lead compensator. Another thing that we have to keep in mind is the second point. The phase to be provided by the compensator must essentially be less than 90 degree and preferably be less than 70 degree. In fact, we saw when we were doing the, when we were actually doing the Bode plot for this, that is, we saw that the amount of phase lead can never be more than 65 degrees. So preferably less than 65 degrees is what we should be keeping, right? So you should not, I mean, sort of do the, take a decision rather, in which case you will be requiring, say, 80 degree of phase lead from your compensator. No, that will not be possible. You will not, numerically, you will never get that much amount of phase lead from your compensator. So you would have to, at the most, settle for 60 degrees or so. 65 would, I mean, 65 or 63, I think we saw, is the most that you would be asking, could be asking for from your compensator. In case you, there is the plant is such that there is no point or no frequency where you can find that out, then you have to abandon the idea of using a single lead compensator. We have to go for other means, right? Other modes. So, okay. So this portion, how many of you have not understood or want me to repeat, or do you have any questions? Because we will actually be doing a numerical where you would be understanding a bit more. But please let me know in case you have any sort of confusion regarding this. No confusion? As clear as water, is it? Okay, let us see as we proceed. So now, again, the same thing. The third point that we want to say is, if we want to use a lead compensator to satisfy the design specifications, we select omega 1 corresponding to the frequency at point A as the gain crossover frequency, so that the compensator will be designed to provide a lead equal to phi 1 and a gain equal to 1 by m1. 1 by m1 would mean that m1. And at the frequency omega 1. So basically this, I mean, what we are saying is, if prior to compensation the amount of attenuation was m1 in the absolute scale, then the amount of amount of gain that we want from our compensator at omega 1 is equal to 1 by that gain, whatever it is, right? Because basically over here, if we are using the absolute scale, this is going to be fractional. Okay, so zero 0.1 or something like that. So 1 by that value is going to be the amount of gain that we want from our compensator. Okay, with the lead compensator, we get a higher gain crossover frequency. It has to be higher gain crossover frequency for the compensator system for the reason that I've already told you. And hence, I mean, if the system gain crossover frequency is higher, the response becomes faster. That is automatically, I mean, a sort of added bonus that we get. So, okay. That is for a lead compensator. Now, I hope you have understood that very clearly, because I will now go to the principle for lag compensator design, and then together we are going to do one single problem where we would be okay, let me without going to the lag compensator right now, let me go to the numerical itself, and then we can come back for the lag compensator. That will be easier for you to understand, I think, because no board work, and I'm feeling a bit sort of cannot understand whether you can understand that is. Okay, so we've now directly come to a numerical where we will assume that we want a lead compensator, right? So over here now, look at the problem. The transfer function of a plant is given as Gs equal to K by S into S plus 5 into S plus 10. Just a moment. Okay, so here now, if you look at that, it is in the transfer function is in the pole zero form. That's fine, but here the gain of the gain of the system is not specified, so it's given in terms of K, right? Now it has been said that you have to design a suitable compensator to meet the following specification. So the kV, that is the velocity error constant value, is specified, as well as the phase margin. So you would recollect that when I in the previous class where we were actually sort of trying to see and derive the expression, etc. I had told you that often this would be the case, or rather, when I was telling you the methods which could be used for compensator design, I had specified that I mean, often we would find that the gain is not really given, but it's indirectly given in terms of the error constants. So here is a problem where that is what we see. Let me just adjust my mask a bit. Okay, so here in this problem, the kV, that is the velocity error constant is specified, as well as the phase margin. So the first job over here, and now, okay, another thing, that is design a suitable compensator. So in this problem, it has not been mentioned whether you have to design a lead compensator or a lag compensator. So we'll be actually using the same problem over here to design a suitable lead compensator first, and later on we will be using the same problem to design a lag compensator as well, to meet the required specification, that is a phase margin of 45 degree and kV equal to 10. So this information now, that is the first information that is provided. From that, what we try to do is we try to find out the value of the gain k for the system. So kV equal to 10 means what? Limit of SGS as S tends to 0 is equal to 10. So from there you can solve and give me the value of k. How much is the value of k? Can you work it out and tell me? This is not related to the compensator design, it's for from the error constants.
500.
Achha. So yes. So this is what we have done. That is kV is equal to limit SGS as S tends to 0, and from there you find that k is equal to 500. So that actually settles your transfer function. So the transfer function becomes GS equal to 500 by S into S plus 5 into S plus 10. So actually the transfer function is given a bit indirectly, just an extra step for you there, but the transfer function is given, I mean fully given, right? So the value of the gain as well as these pole locations, etc., are given to you. So now comes the second part, that is you, the specification is that I mean the phase margin should be 45 degree, and you would have to design a lead compensator now. Okay, so for that now we will be seeing what the steps are, right? So the first step that I told you is that you would have to tabulate the gain versus frequency and phase versus frequency for this particular system, because we want the Bode plot, right? So Bode plot means the gain versus frequency and phase versus frequency. We are not actually going to do a plot as such, not a graphical plot at least, but we are going to tabulate the value of the gain versus frequency and the phase versus frequency for this particular system. So say for example, for a frequency omega of 1 radian per second. So I'll just go to the previous slide. So omega equal to 1 radian per second is the value of frequency for which we would require to calculate the gain value and the phase value. Can you do one at a time? So now the expression for gain you are familiar with from this. So you put S equal to j omega and then find the magnitude for magnitude of GS. From there, now you place, I mean, you substitute omega equal to 1 radian per second and calculate the magnitude value. How much is going to be the magnitude value for omega equal to 1 radian per second? Can you just do that and tell me so that I mean, I know that you have understood that much. If you want me to repeat, I'll repeat, because I mean, no problem that way.
Yes, ma'am, please repeat.
Achha. So GS is given, right? So GJ omega you can find out putting S equal to J omega. Then you can find
Yes,
out the
ma'am.
magnitude of Gj omega. How to find out the magnitude of Gj omega? You have to find out the magnitude of this. This means when S equal to J omega. So that now magnitude will be how much? You have 500 in the numerator. In the denominator, first of all, you have J omega, then you have J omega plus 5, then J omega plus 10. So you have to find out the magnitude over there as well. So once you find the expression for magnitude, put omega equal to 1 radians per second. So basically, from there, you would be able to calculate the value of the magnitude at omega equal to 1 radian per second. So I now want you to find the value and tell me. What is the expression for magnitude first of all? You have in the numerator 500 by here now omega into root over of omega square plus 5 square and then root over of omega square plus 10 square, right? So basically now omega equal to 1, so find the value.
9.75.
Let me see. 9.75. Now you have
Or
given it in decibels, so I want it in decibels. Now 20 log to the base 10 of 9.75 is what you have to do.
19.78.
Acha. Yes. So 19.79 is what the magnitude value in decibels is at a frequency of 1 radian per second, right? So that actually verifies this entry over here. Similarly, now the phase for this at omega equal to 1 radian per second. When you are computing, of course, you are going to calculate all the magnitude values first and then the phase values, fine, no problem. But now, just to start off with, we would want to calculate the value of the phase at 1 radian per second. So now, how do you do that? What is the contribution to the phase from this numerator over here? Pure gain. How much of phase contribution from 500? Pure magnitude কত phase থাকে? What happened? What we have to do is s equal to j omega that we have put. Now I want to first of all, I mean, sort of understand how, I mean, what will be the expression for the phase, and then from there you can put omega equal to 1 radian per second, fine. So now for that we would have to find the contributions to the phase from each of the terms over here, right? So first for the 500 in the numerator, how much of phase contribution from there? বোঝো কাণ্ড, পিওর গেইনিং ফেজ থাকে? This numerator, that is 500, is a pure gain, so the amount of phase contribution from this is 0 degrees, nothing else, right? Now what will be the first term is s equal to j omega, I've put over there, so j omega. From that, what is the phase contribution? How much of phase contribution from 1 by j omega, that's in the denominator. So how much of phase contribution from this first, that is j omega, that I get when I put s equal to j omega? How much will it be? এই কমপ্লেক্স নাম্বার ফার্স্ট ইয়ারে পড়িয়েছিল, ফার্স্ট ইয়ারে না, এখন 11-12 পড়ায় বোধহয়, তারও আগে পড়ায়। How much of contribution from 1 by j omega to the phase?
minus 90 degree.
তবে so it is going to be minus 90 degree contribution to the phase from this first 1 by s, that is right. So the phase is 0 degree, that is from the 500. Need not write, but just to, I mean, sort of keep matters very sort of all everything cleared in front of your eyes, that is. So 0 degrees minus 90 degrees and then the contribution from this one. So j omega plus 5 is what you have over here as this term. So how much of contribution from this?
Minus tan inverse omega by 5.
Hmm? Let me do something. I'm just trying to write a bit over here. না লিখলে এমনিতে বোর্ড ওয়ার্ক করা যাচ্ছে না। Moment. Okay, just look at this. I've now put, just shifted a bit, doesn't matter. Just to explain things, can you see I've written some new things? I've put g j omega. I've put s equal to j omega over here so that you understand what I'm speaking about. And that makes it 500 by j omega into j omega plus 5 into j omega plus 10. I've used w instead of omega, but anyway. So now what we are trying to do is, if we have a complex quantity as a plus jb, how much is the phase? What is the expression for phase from this? How much will it be? A plus jb. What is the contribution to phase from this?
tan inverse b by a.
Yes, isn't it? So that is, I'll just write it so that everyone understands. Tan inverse. Just a moment. The phase from this, not this, of course. I have not written all that. So the phase contribution to, I mean, from this, that is a plus jb, is tan inverse of b by a. Of course, you already knew that, just a bit rusted, or I mean, some fungus on that, whatever it is. So now, I mean, if I have this j omega plus 5 in the denominator, how much will be the contribution to the phase? What happened now? You have 5 plus j omega, if I tell it that way, right? So 5 plus j omega will be how much now the phase contribution will be? If I just look at the 5 plus j omega, it would have been tan inverse of omega by 5. But because it is not 5 plus j omega, but 1 by 5 plus j omega, so the phase contribution will be minus of tan inverse of omega by 5. Isn't it so? Right? So from this term, that is j omega plus 5, the contribution to the phase is minus tan inverse of omega by 5. Similarly, from the last one, that is this j omega plus 10, the contribution is going to be minus tan inverse of omega by 10. So overall, if I look at the phase from this, I'll just write that because it doesn't seem that you are very much comfortable with it. So that's why let us just write it. Tan inverse of, okay. Right. So the phase contribution, or rather the phase, yeah, the value of the phase at any frequency omega is going to be 0 from this one, not written, minus pi by 2 over here from the j omega, minus tan inverse of omega by 5 minus tan inverse of omega by 10. The minus is coming because these are from the poles, that is in the denominator, not from the numerator, right? So that is the expression for omega, sorry, for the phase phi for a frequency or at a frequency omega, at any frequency omega. So now from that expression of the phase, we have to compute the phase values at respective frequencies, starting with 1 radian per second as we stated. So now I hope you would be able to calculate for 1 radian per second. Now if you have not understood this, I may try to repeat it if you want, but I think it is sort of understandable right now. So what is the value of phase for at 1 radian per second, for a frequency of 1 radian per second? How much is it? What happened? Is anybody trying it out? What happened? No answer. Anyway, so basically, I mean, once you get the expression, if you put in a particular value of frequency, say 1 radian per second, you would be able to get the value of the phase in radians, or you can convert it into degrees. So basically, over here, the value of the phase is actually computed in degrees. But I would actually request you, at least one or two of you, to work it out and verify whether you are getting the value, so that you understand that yes, that is the value that we get. Otherwise it's going to remain vague. I can just show you the table and move on. It's going to save my time, but it will not serve the purpose, in this sense that you will not be able to be confident that okay, that is what we get. So just verify and tell me at least one value, and then we can proceed. Yes, Rajwan has written it. Good. So it will be 107.02 decibels. Okay, so basically, once you are able to verify that particular value, now corresponding to any frequency, once you get the expressions, I have not written the expression for the magnitude, but I've verbally told you, and the expression for phase, corresponding to any frequency omega, you would be able to compute the phase value and the gain value, right? So by, I mean, the same method, what has been done is corresponding to different frequency values, the phase and the magnitude has been calculated. Magnitude in decibels, phase in degrees, right? So this is a table tabulating the, actually it's going to give you the Bode plot. If you do a plot, I mean on a graph paper corresponding to this, the magnitude versus frequency will give you the magnitude Bode plot. Phase versus frequency is going to give you the phase Bode plot for the system which is given to you, meaning this particular system 500 by s into s plus 5 into s plus 10, right? So the tabulation of the frequency response is in front of you. So now what do we, I mean, do with this table? We would have to look at this table and then try to understand where to place our or for that matter, where not to place the desired gain crossover frequency to start off with. So now please try to be a bit interactive, and I mean, let me know whether you have actually understood what I've said earlier. So now here I look at this magnitude value, it is 19.79, and I'm looking to place a lead compensator. So from the lead compensator, I will be getting a positive decibel value of gain, right? So can I place my lead compensator at a frequency of 1 radians per second? No, because the moment I mean, I want to place some lead compensator. So lead compensator means I'm going to get some positive value of gain from there. So that positive value added with this 19.79 is not going to make this frequency, it cannot be made the desired gain crossover frequency, because gain crossover frequency means what? At that particular frequency after compensation, I want the gain value to be equal to 0. So I cannot place it at 1 radian per second. Similarly, at 2 radians per second, it is plus 13 decibels. So I cannot place my lead compensator at 2 radians per second either, right? At 3 radians per second now, I still have a positive value, that is plus 8 decibels. So I cannot place my desired gain crossover frequency if I'm using a lead compensator over here. Similarly for 4 radians per second, right? Now this value, that is 6 radians per second, at 6 radians per second, I find that I have got over here a minus 0.772, I mean, is the value of the gain of the original uncompensated system, that much decibels, right? So I can, though it is a very small value, and I would normally like to sort of avoid it, because basically it is a very small value and numerical problems may arise if I want want to place the compensator at this particular frequency. But apart from that, now if I place the lead compensator at 6 radians per second, what would be the amount of gain that I would be wanting from my compensator? The amount of gain that I would be wanting from my compensator would be equal to plus 0.772 decibels. Compensator is applied on the uncompensated system, overall magnitude at this particular frequency, that is 6 radians per second, becomes minus 0.772 plus 0.772. That is going to give me a 0 decibels. So I can actually, theoretically at least, I can place my desired gain crossover frequency at 6 radians per second. So of course, over here, the value that I ask for will be very small. That's of course there, but I can do it. Similarly, now at 8 radian per second, the amount of gain from the uncompensated system, gain of the uncompensated system, is minus 5.7, right? So if I place my lead compensator at 8 radians per second, the amount of gain that I would be wanting from my compensator would be plus 5.725 decibels. so that overall, after the compensator is applied on this system, the gain value is going to be minus 5.7 plus 5.7, which is going to be 0 decibels, and that is going to make 8 radian per second the gain crossover frequency of the compensated system, right? So similarly, for this 10 radians per second, I can place it at 10 radians per second. So to summarize, I can place my desired gain crossover frequency anywhere above, at or above, I can say 6 radians per second, right? Because over there, at least from the magnitude consideration, the gain sorry, gain value is already negative. So if I put in my lead compensator, I'll get a positive positive gain contribution from that, and overall I can make any of these frequencies the desired gain crossover frequency. Now, apart from that, there is another consideration that I have to look at. So, okay, from the gain point of view, I can place my lead compensator at or above 6 radians per second. What about the phase? So now, just see what the desired phase margin was equal to 45 degrees. So that is the requirement, the specification that I must meet after the compensator is applied is a phase margin of 45 degrees, right? So now, if I place the lead compensator, say at 8 radians per second, now at 8 radians per second, the phase of the uncompensated system is equal to minus 186.65, right? Now, is that suitable so that when I apply the lead compensator along with the uncompensated system is going to give me the desired phase margin, that is the specified phase margin that I want. So ultimately I want 45 degree of phase margin. So 45-degree of phase margin means what? Ultimately my phase plot should have a phase value of how much? Phase value should be minus 135 degrees, so that the difference with minus 180 degree is equal to 45 degree. That is the phase margin, isn't it? So the phase plot should basically be having a phase value of minus 135 degree if I want a phase margin of 45 degrees. But here I have to keep in mind that I would be asking for some amount of phase lead from my compensator as well. So let us see what will happen if I place the lead compensator at the GCF of the desired GCF, I mean, at 8 radians per second. What will be the value of this? That is, what will be the amount of phase lead that I want from my compensator. So in order to do that, I would have to recollect this, that is the plot, that lead compensator plot over here. So this is going to be this minus 180 degree plus PM minus phi 1. This is the phase that I'm looking at, and that is equal to say minus 186 at 8 radians per second, right? So what will be the amount of phi 1? What will be the value of phi 1 that I want? So that will be minus 180 degree plus PM will be minus 135 degrees for us. So minus 135 degree minus phi 1 is equal to minus 186. So can anybody tell me, I mean, how much my phi 1 will be? এখানে দেখিয়ে বলছি তোমাকে। This is the thing that I'm trying to state. That is, at omega c equal to, if I place my desired gain crossover frequency at 8 radians per second, what will happen, right? So as far as the gain is concerned, I will be looking at a gain of plus 5.7 from my compensator, which I can get. As far as the lead is concerned, now how much of phase lead would I want from my compensator? That is what I'm trying to calculate. So originally, now for the uncompensated system, the phase was equal to minus 186 degrees. Now the amount of phase lead that I want from my compensator would then be rather equal to that 186.65 minus 180 degree minus 45, which is 135 degrees. So the difference, that is 186 minus 135, will be the amount of phase lead that I want from my compensator, right? Did you understand this portion? So originally the phase at 8 radians per second was minus 186, but I want it to actually give me how much? I want it to give me minus 135 degrees ultimately, so that my phase margin is equal to 45 degrees. So mine that 186 that I had earlier minus this, that is 135 degrees, or you can say minus 135 minus minus 186, that is minus minus makes it plus actually. So when I do that, ultimately the amount of phase lead that I want from my compensator boils down to 51.65 degrees. So if I want to place my compensator at compensated system GCF at 8 radians per second, the amount of phase lead that I would be wanting from my compensator would be around 51.65 degrees. We can try to obtain that. So in that case now, you would have to actually now, put in your parameter values, that is omega c is equal to 8 radians per second, phi suffix c is equal to 51.65 degrees, and mc is equal to plus 5.725 decibels. So from there now you can just put it in the, that is the first step completed. You can just put it in the quadratic and obtain the value of alpha, and hence obtain the value of a for those values, right? Similarly, if the if the frequency is, the desired gain crossover frequency is chosen as 10 radians per second, what is the situation? So the amount of gain that I want from a compensator is plus 10, so that this minus 10 and plus 10 makes it equal to 0 decibels and makes that frequency the gain crossover frequency. Now, as far as the phase is concerned, the phase was originally minus 198 degrees, and I want the compensated system phase to be minus 135 degrees, so that basically the phase margin becomes 45 degrees, right? So what is the difference of that minus 135 with the minus 198? So minus 135 minus minus 198 will be 198 minus 135, which is equal to around 63 degrees. So basically this is also obtainable, but just a borderline case. You would recollect that we said 63, 64 is the maximum amount of phase lead that we could ask for from a compensator. Otherwise, what will happen is numerically you will not be able to obtain a solution, you will not be able to obtain a value for the a and alpha. It will not be a feasible value that you obtain if you are choosing unrealistic values. Say if you ask for 80 degrees or 70 degrees, for that matter 75 degrees, then you will not be able to get a solution, proper solution for your quadratic, and there will be no feasible solution that you would be getting. But yes, over here then the GCF can be, desired gain crossover frequency can be placed anywhere between 8 radians per second and 10 radians per second. On purpose we have avoided 6 radians per second, because for 6 radians per second, again also because the magnitude requirement is very very small. From the compensator you want only plus 0.772 decibels. There also numerical problems may be arising. We normally would not want it to be lesser than say 2 or 3 decibels, not lesser than that at least. So basically uh, Otherwise, numerical problems may be arising. So we are avoiding 6 radians per second as the desired gain crossover frequency for that reason from the magnitude point of view. On the other hand, from the phase point of view, we see that okay, 8 radians per second to 10 radians per second, but not beyond 10 radians per second, because in that case, what will happen is the phase will monotonically be more and more negative. So the phase beyond 10 radians per second will be more negative, and the amount of lead that you want from your compensator will be greater than this 63 degrees. So basically, it is again going to be something that you will not be able to get even if you ask for from your lead compensator. So this actually completes the design for the lead compensator only. Now tell me whether you have understood what we have discussed over here. Otherwise, I mean, it will be creating a problem when I go to the lag compensator now. I'll just finish off with the lag compensator as well. Give me another half an hour or so that we finish off today. But before that, let me know whether you have actually understood the lead compensator properly. If you have any questions, please feel free to ask, because as I told you, Shamna Shamni Bulchina Bole, I am feeling a bit awkward as well, because when I do board work, lots of scribbling and this and that. So, I mean, and I can also make out whether you are understanding or not, but over here, that's not possible. So, please feel free to let me know whether you have understood. Not many figures as well, only 2 or 3 figures that I've used over here. Nothing to, I mean, nothing extra that I can do much over here. Should I proceed with the lag compensator now? I mean, without any answer, also I'll assume a positive from your side.
Okay, ma'am.
Okay. अच्छा, ठीक है. So now we will look at the principle for lag compensator design. So again, over here now you have you see two plots, one on the left hand side and the other on the right hand side. Left hand side plot being a general plot for any system, right? So I mean, actually it is going to be, I mean, this corresponds to the tabulated I mean, frequency versus phase and frequency versus gain. So in that case, it's going to be some sort of plot like this, right? So a generalized one is what we have put over here. On the other hand, on the right hand side, we have the asymptotic magnitude and phase plots for Bode response for the lag compensator. This we had done in the previous class, right? So now again, uh, for the sorry, for the lag compensator, we would have to realize certain things. One is that the magnitude plot is over here. So the magnitude is either 0 decibels or it is a negative decibel value. Some other people appearing. So it is either 0 dB or it is a negative contribution as far as the magnitude is concerned, right? So now, I mean, without going further, if I want to place my desired gain crossover frequency over here, what would be the range that I would be able to choose as my desired gain crossover frequency? Now, the magnitude contribution from the lag compensator is essentially negative or 0, right? So, unless I choose a value, or rather, yes, a value of frequency where the magnitude is already positive, that positive plus the negative can give me the 0 value of decibels. But unless I do that, I will not be able to place my desired gain crossover frequency where the gain was originally negative. Originally means the uncompensated gain was already negative. Now, if I put my compensated system, compensator, actually, compensated system, if I put my compensator, that is going to contribute a negative gain again. So the negative gain plus the negative gain cannot make the gain of the compensated system 0 decibels at any frequency. So in this range, that is, this was the original gain crossover frequency, original meaning the uncompensated system gain crossover frequency. So I cannot put but the desired gain crossover frequency beyond the gain crossover frequency of the uncompensated system. So I have to choose the desired gain crossover frequency lower than the original, that is uncompensated system gain crossover frequency, such that if, say, for example, I choose omega 2 as my desired gain crossover frequency, the magnitude over there being equal to plus m2 now, from my from my this lag compensator, I would be wanting a minus m2. Here, the absolute values are shown over here. That's why m2 and 1 by m2 is written. So minus m2 contribution from the lag compensator and at this particular frequency will make the overall gain equal to m2 minus m2, which is equal to 0 decibels, which would be able to make this frequency omega 2 my modified or desired gain crossover frequency of the compensated system, right? So this is the range that I should be looking at from the gain point of view. Now, as far as the phase is concerned, what is the issue? Now, over here, okay, so the phase from the lag compensator essentially is going to be a phase lag, meaning a negative phase contribution, right? So if there is a desired phase margin that I have in mind, which is denoted as PM, say, then I would have to now scan the entire phase margin where the phase margin or else where the difference with the minus 180 degree is equal to pm plus phi 2, or in other words, if I look at the phase value, which is what we are going to do actually, the phase value at the desired gain crossover frequency should be equal to minus 180 degree plus pm plus phi 2. Why? Because the moment I put in my lag compensator, the amount of phase is going to be increased in the negative sense. That is, along with this, minus phi 2 is going to be added, right? So that then the phase value will become minus 180 degree plus pm plus phi 2 minus phi 2, which is equal to minus 180 degree plus pm, and that would make the phase margin on this side, that is the difference with the minus 180 degree, will be equal to pm, right? So I'll repeat that. I take an additional value of phase margin over here, so that when I put my lag compensator, that additional value and the lag that I get from my compensator will be neutralized, so that we will get the desired phase margin as the value of the phase margin, which is going to be computed at the compensated system gain crossover frequency. So with that, now, if you have understood that, we proceed to our numerical problem, but this time I would be wanting the answers from you. Just try to say, because that will help you as well as it will make me understand whether you've understood. So our system is the same system. We've already calculated the frequency response table. Table remains same for this problem as well. This problem means the lag compensator design. For the same system, we are going to design the lag compensator. So now, from the magnitude point of view, we are looking at the lag compensator, right? So lag compensator means a negative decibel value is what we are going to get from our compensator. So that now, if I ask you what would be the range of frequencies where you wish to place your desired gain crossover frequency, you can see that, okay, up to 4 radians per second, let us say 4 radians per second. What is the value of the magnitude that you have got? It is plus 5 decibels. Now, from the lag compensator, you can ask for minus 5 decibels, so that overall you can place your desired gain crossover frequency over there, right? Similarly, if you place your desired gain crossover frequency at 3 radians per second, you would look for minus 8 decibels of gain from your lag compensator. So the entire range over here has positive decibels magnitude, which will be which will help us to actually put in our lag compensator anywhere within this range, at least from the magnitude consideration, so that we can ask for exactly that much negative lag negative gain contribution from the lag compensator, right? Now, of course, the phase consideration has not been done so far at all, for this at least. So from the lag compensator, we are going to ask for a phase lag, that is minus phi 2 is what we would be asking, right? So the specification remains the same, meaning we still want 45 degrees of phase margin, right? Now, if I look at this frequency, just to start off with, 4 radians per second. Now, here you can see what is the value of phase that you see. It is minus 150 degree. If I want a phase margin of 45 degree, how much should be my phase value? How much should be the phase value of the compensated system if I have a 45 degree phase margin? এটা বলো তাহলে বুঝতে পারবো বুঝেছো কিনা। না 225 না, I want 45 degree 15.6 now 15.46 on a 15.46 is what I mean right now I'm asking if I want a phase margin of 45 degrees, how much should be the phase value? You are possibly you've calculated one step further, I think. How much should be the phase value at 4 radians per second if I want the uh, desired gain crossover frequency at 4 radians per second? And sorry, if I want a 45 degree phase margin, how much should be the phase value at that particular frequency? Minus 15 টা কি? All of you are saying minus 15. Minus 15 is what? 45 degree of phase. Achha, just let me go to the plot once more. Tell you what I'm trying to ask for. What I'm saying is the phase margin that I want, forget about this minus 5 1 and whatever. The difference with minus 180 degree is the phase margin, and that is 45 degrees as specified for us. So if this is 45, then I mean, how much is the phase value? Phase value means what? The rest of it. So I mean, if minus 180 degree minus this is basically equal to 45, then how much is the phase value? Is it not minus 135 degrees? ফেজটা যদি minus 135 degree হয় তাহলে difference with minus 180 degree is going to be 45 degree. Is it not so? Here I'm not asking for the lag compensator at all right now. I mean, the question that I asked was, if the phase margin that I want is 45 degrees, how much should be the phase value that I would be, I mean, looking at? It would be minus 135 degrees, because when the phase is minus 135, then the phase margin is minus 135 minus within bracket minus 180 degree, which is equal to plus 45 degrees. Is it not so? So the phase value should have been minus 135 degree. Possibly Anita and Moshmi, I think you answered the next question that I'm going to ask. So the amount of, but that is also not very correct. What you've answered is not really correct. Now, if now have you understood what I said so far regarding the, if the phase margin that I want is 45 degree, what should be the phase value at that particular frequency? It should be minus 135 degrees, so that minus 135 and the difference with minus 180 degree is 45 degrees. Okay. Did you understand that portion? Just let me know whether you understood or not. Just that portion. If I'm looking for 45 degree of phase margin, the value of phase should be minus 135, so that the phase margin is equal to minus 135 minus 180 degree, which is equal to minus 135 plus 180 degree, which is equal to 45 degrees of phase margin. Is that clear? এটা বুঝলে কিনা বলো?
Yes, ma'am.
Right. So minus 135 degrees is what I'm looking for ultimately from the compensated system. After I use my compensator, my phase value, okay, should be minus 135 degree. Now, for my system, it is already minus 150 degree, and I'm going to use a lag compensator. So lag compensator will give me a negative phase contribution. Is it not so? So from the minus 150 degree, if I wanted to, wanted to go to minus 135, can I use a lag compensator at this particular frequency to give me a,
No, ma'am.
minus 135 degrees over here? Isn't it? So at this particular frequency, it is already more negative than I wanted. And from the lag compensator, I will get more lag. So I cannot actually use the lag compensator at 4 radians per second. Is this portion clear, right? So I hope all of you have understood this. If not, let me know again. That is, the at 4 radians per second, the phase is minus 150 degrees, right? But for 45 degree of phase margin, basically, ultimately, I would be wanting the phase value to be minus 135. So if I use a lag compensator at this frequency, I will get more negative, phase. So I cannot, if I add that with this, I can never go to minus 135, isn't it? So that actually rules out this possibility, that is 4 radians per second cannot be my desired gain crossover frequency. Though from the magnitude point of view, it could have been possible, but I will not be able to use the lag compensator, because by using some amount of lag, I can never push up my phase margin to 45 degrees, right? So similarly, now if I look at 3 radians per second, so here the phase value is already minus 136 degrees, which actually is, I mean, again, if you look at this, it is, if I take the difference with minus 180 degree, it is equal to 44 degrees, lesser than 44, in fact, 43 point something. So by using the lag compensator, it's going to become, this phase value is going to become more negative, meaning the phase margin is going to be even lesser. So again, for 3 radians per second, I cannot, use a lag compensator, because ultimately I want 45 degrees of phase margin, meaning I want a phase of minus 135. With the lag compensator, I can never, I'll get a negative value of phase from my lag compensator. So adding that to this, I cannot make it minus 135, right? So that is why I have to use a lag compensator at this particular frequency to give me a negative gain crossover frequency, right? So similarly now, for 2 radians per second. So 2 radians per second, now what happens? I have a positive value of magnitude, that is 13.16. So I can place my compensator from the magnitude point of view. I would be wanting minus 13 decibels of magnitude from my gain from my compensator. Fine. Now, as far as the phase is concerned, what happens? I have a minus 123 degrees over here from the uncompensated system. Now, if I put in my compensator over here, so that at 2 radians per second, how much of phase, if I, how much of phase lag would I want from a compensator, so that finally the compensated system phase margin will be equal to 45 degrees. So phase margin being 45 degree means ultimately the value of the phase is going to be minus 135. So you can just say how much of lag, added lag, will make this equal to minus 135 degrees. So how much will that be? That will be, you can see that around 12 degrees or so. Just, vaguely I'm saying, without considering the decimal point. Okay, so minus 12 degrees of phase lag from the compensator, along with this minus 13 decibels, can make me, use this frequency, that is 2 radians per second, as a possible frequency where I can place my lag compensator. Similarly now, this 1 radian per second, if you look at that magnitude point of view, it's okay. I want minus 19 decibels from my compensator. From the phase point of view now, I would be wanting how much? You can see that. So I mean minus 135, and then here it is minus 107. So around just how much will it be? 20 something will be the amount of phase lag that I want from my compensator, right? So here an additional frequency has been inserted, 2.5, where also you would be able to use that frequency as your possible or desired gain crossover frequency, so that you can ask for about 5 degrees of phase lag from your compensator, and similarly the gain. So with that, now I'll just go to the written things. So this was for the lead, actually calculate courage. So now at 2 radians per second, as we were saying, the amount of phase lag would be around 11 degrees. So 135 minus 123 will be 11.89, where the amount of gain we require from our compensator is 13.16, right? So that if we choose 2 radians per second, our omega c will be 2 radians per second, phi c will be minus 11.89, and mc will be equal to minus 13 decibels. So now again you put it in your quadratic, solve for beta, and b, you will be getting your compensator, right? So okay. So here, I've gone back to the lead compensator. Lead compensator, the values have been computed for a specific frequency. If we choose omega c equal to 8 radians per second, then the lead compensator lead to be provided is 51 that we just saw earlier, and the amount of magnitude contribution would be around 5.7. So the computed values after solving the quadratic. So you put that in the quadratic, you would recollect that quadratic. I'll show you the same thing that we saw in the last class. This one, okay, so this quadratic now, so q, this is the quadratic, so q is equal to tan alpha, that can be calculated. C is equal to a square, okay, 10 to the power of mc by 10, where mc is the value of the magnitude in decibels. So c also can be calculated. So calculate, I mean the sorry, coefficients of alpha square and alpha and the constant term, and then you will just get a numerical, that is a quadratic equation in alpha. Solve for alpha, you will just get two possible values, one of which you will see is feasible compared to the other one, and maybe the other is not at all feasible, whatever you find. So from there now you would be able to find alpha, as well as now once alpha is found out, put it in this expression and find out a. So the remaining part is just mechanically calculating by putting the coefficients of the quadratic and then solving for alpha, and then substituting in this equation, getting the value of a. That was for the lead compensator. Similarly, for the lag compensator, once you decide on the values of your omega c, mc, and phi c, you would be again able to calculate q and c and then solve for the quadratic. So here again, this is the lag compensator that I'm showing. Q is equal to tan phi c, and c is equal to 10 to the power of mc by 10. Those two remain the same. And so you can put in those and then try to solve for beta. Once you get the value of beta, you solve, you not solve, you substitute in this equation and get the value of b. Once you get beta and b, your compensator is going to be given by compen- compensator is going to be given by beta into s plus b by s plus beta b. So beta and b being found out, you will be able to find out GCS. So the remaining part also, the remaining part means, sorry for switching slides, but so this is the lead compensator. Once you decide on which frequency to place your desired GCF, you will be able to put in omega c and phi c and mc, and from there the transfer function can be found out for the compensator. Similarly, for the lag compensator, lag compensator, the value of the transfer function has been found out by finding the beta and p values, right? So what I would like to mention next is that one thing is to be kept in mind. This problem is a design problem, right? So design problem means there is no one correct value which, I mean, everybody would be using and getting the answer, right? So there is a range of values or range of possibilities within which, I mean, any one value can be chosen, many meaning that the frequency where you want to place your compensator, the desired gain crossover frequency, as I have been mentioning, somebody may choose at, I mean, a particular frequency, somebody else may choose another value, somebody may be choosing a third value. All the values that you choose, provided the principle is correct, would be considered as correct. So there is no one unique value of compensator that you would, that all of you would have to get essentially, but depending on the frequency that you have chosen as your desired frequency where to place the compensator, accordingly your solution should be correct, right? So that is as far as the lead compensator and the lag compensator designs are concerned. Now, in case you have any queries regarding this, you can ask. Otherwise, I'll just proceed a bit more and finish off this portion. Not much that I'm going to do. If you have any questions, you can ask, please. Okay. So, uncompensated system, just raise a hand or something and let me know. So, the uncompensated system response is shown over here. The lead with the lead compensator, you can see that the response becomes faster, the green response, just to show what is happening. And you need not plot it as such, but in case you are interested, you can see by addition of a lag compensator, response becomes slower, and this is the red one is the time response. Now, coming to the lag lead compensator. Now, okay, so as far as the lag lead compensator is concerned, um, till so far what we had done is a pure lag compensator and a pure lead compensator. And in fact, as far as numericals are concerned, as far as understanding is concerned, if you understand the pure lag and the pure lead, you should also be able to do the rest of it, meaning the lag lead and the lead lag. So now over here, the lag lead compensator transfer function is given to you. Now here basically the location, relative locations of the poles and zeros is very, very important. So here basically alpha into beta is equal to 1, alpha is greater than 1, a is greater than b. So if these are the parameter values chosen, or relative values are chosen in this fashion, then the pole zero locations are going to be like this, meaning that the one pole is going to be to the far left, then the two zeros sandwiched in between, and finally the last pole will be the closest to the imaginary axis. So the relative positions of the poles and zeros is very, very important. It doesn't matter if, I mean, say for example, this minus b value is shifted a bit more to the right or a bit more to the left, the compensator will still remain a lag lead compensator. But if, say for example, this zero goes to the left of this minus alpha a, then the relative values will become slightly different. So say for example, 1 pole 1 0, then it is no longer going to remain a lag lead compensator. So this can be understood best from the frequency response itself, which is in front of you. So now, I mean, since you have this, the value of alpha into a product is the, I mean, is the largest, you can say. Basically, as far as the corner frequencies are concerned, you can see from this transfer function that there are 4 corner frequencies. One is at beta b, and then the one at b, and then a and alpha a, right? Relative values being like this because a is greater than b, and you have alpha greater than 1, as well as alpha is equal to 1 by beta. So basically, the relative locations of the corner frequencies are going to be exactly in this order. So if it is in this order now, basically the first corner frequency, that you encounter is basically beta b.
So beta B corresponds to a pole. So pole means what? From beta B, the plot is going to go down at minus 20 dB per decade. Go down till what frequency? Till the next corner frequency, that is B. Now B corresponds to a 0. So 0 means what? The minus 20 dB per decade with the plus 20 dB per decade is going to make the plot go parallel to the frequency axis. That is, it is going to have a constant magnitude over here. Similarly, now the next corner frequency, which is A. Now A corresponds to a 0. So 0 means what? Again, you are going to get a plus 20 dB per decade from that frequency. So the plot goes up like this. And again, it goes up till the next corner frequency, which is alpha A. Alpha A corresponds to a pole. So pole means what? Plus 20 dB and minus 20 dB. Basically, pole means what? It's going to go down at minus 20 dB per decade from that frequency. So that minus 20 dB per decade with the plus 20 dB per decade is going to make it a constant value of magnitude. So basically, this is the asymptotic magnitude plot for the system. As I told you, for the case of the pure lead and pure lags, compensators as well. Basically, the exact plot is not required as far as the module is concerned, simply because of the fact that exact plot can actually be drawn. Number one, from the asymptotic magnitude plot. Number two, from the expressions. We had not actually, we are doing the plot just to get a feel of the thing, meaning that to understand qualitatively what is happening. Quantitatively, if you want the values, naturally you are going to use the expression for the magnitude, as we did for our numerical problem. And similarly, for the phase, you are again going to use the expression, corresponding expression. So basically, the magnitude plot, asymptotic magnitude plot, drawing of the asymptotic magnitude plot is sufficient for this. Similarly, now for the phase, initially, the expression for the phase is what? You can say for example, okay, if I look at this form, so the first, when I go by the same method, that is S equal to J omega is what I do first, and then I look at the individual contributions to the phase, right? So from here, the contribution to the phase will be plus tan inverse of omega by A. Then the contribution from here will be plus tan inverse of omega by B. Contribution from here will be minus tan inverse of omega by alpha A. And contribution from this will be minus tan inverse of omega by beta B. So those are the four individual contributions to the phase. Now, of course, at a very low frequency, that is omega tends to 0. So tan inverse of 0 plus tan inverse of 0 minus tan inverse of 0 minus tan inverse of 0. So at a very low frequency, the phase value will be equal to 0. So it will tend to 0 at a very low frequency. Similarly, at a very high frequency, what will happen? So contribution from this, if it is, tending to a very high frequency, means omega tends to infinity. So what will be the contribution from this, 0? Tan inverse of omega by A, and omega tending to infinity. So how much will be the contribution to the phase? It will be plus 90 degree. So plus 90 degree from this, plus 90 degree from this, minus 90 degree from the denominator first term, and minus 90 degree from the denominator second term will make it overall 90 plus 90 minus 90 minus 90, which is 0 degree. So you can see that ultimately the phase is going to again tend to 0 degree. Now, intermediately, of course, first of all, we see that the first corner frequency that we encounter corresponds to beta B. Beta B corresponds to a 0. So 0 means what? Basically, it 0 corresponds to a pole. So pole means what? Pole has a negative contribution to the phase. So basically, of course, we have to, from the expression for phase, if you calculate, if you put in a particular frequency value, you will be able to calculate how much of phase is coming in. But what we can see is the nearest corner frequency is corresponding to a pole. So ultimately, when you add together all those contributions, it is going to go more negative compared to what it was earlier, meaning 0 degree. From 0 degree, it is going to go to the negative side. Next, of course, you have the next corner frequency, which is B. B corresponds to a 0. So 0 means what? It is going to actually try to go up. Up means a positive, go to the positive side. Similarly, now the next one is again a 0. So it's going to go more up, and then finally the pole at alpha A is going to make it go down, and it's going to go to 0 degree. So what I said just now is just a qualitative feel. Of course, you can numerically calculate and see for yourselves whether the phase is going to go first to the negative value and then to the positive value. Intermediately, somewhere it's going to have a zero value as well. So that is the nature of the phase plot. Something that I wanted to, tell you regarding this before going further is that basically this compensator is known as a lag lead compensator. So the name actually comes from the fact that the lag comes prior to the lead. Prior means at a lower frequency, it starts with a lag portion, and then the higher the frequency, it goes to the lag. So a lead lag compensator, in a lead lag compensator, from the name itself, we will know that the lead portion, that is a positive value of phase, will come first and then the lag will come. So lead lag means first the lead, then the lag. Lag lead, as over here, means first the lag, then the lead. First meaning at lower frequency, it's going to start with the lag, and as the frequency increases, it goes to the lead. That is it, right? So that is as far as the lead compensator is concerned. Now we have already done the principles for rather we have found some expressions, and from there we know how to do the design for the pure lag and the pure lead. Now over here, similarly, okay, this is the lag lead compensator. It is in the lag lead compensator again. What you would be, design of the compensator would be amounting to finding out the value of A and alpha and B and beta, right? So that a desired, gain phase margin would be provided at a particular frequency and at, with a gain of some value. So just go through these points quickly before winding up. Achha. It is desired to find out A, B, and alpha so that the system may provide the specified phase margin frequency omega c. Now, if we want a positive contribution from the magnitude and the positive value of phase lead from the compensator, we would have anyway used a lead compensator. Why would we go in for some other compensator, right? So if we are going in for designing a lag lead compensator, it would imply that we would be asking for a negative value of magnitude where we want, where we get a, where we are asking for a lead parallelly. I'll repeat that. I'm saying that pure lag compensator or a pure lead compensator, we have seen that, say for example, in a pure lead compensator, gain value is positive and gain phase value is also positive that we get from the compensator. For a pure lag compensator, gain value is negative and phase value is also negative that we want. So basically, if we want a say a positive lead, that is a lead and a positive gain, we are anyway going to go for a lead compensator. Why go for lag lead compensator? So lag lead compensator will be used only when, say for example, if we want MC, that is the magnitude, to be negative, but simultaneously for the same frequency a lead to be required. Meaning, say if we choose omega c as the frequency, the magnitude contribution must be negative, whereas the phase contribution must be positive. So only in such a case, the lag lead compensator we would want to go for, right? So if that is the case now, basically, if we want a phase lead means what? For a lag lead compensator, we've seen that at the lower frequency range, we are getting a lag over there. So that will not serve our purpose. We would be wanting a lead from the compensator. Lead from the compensator means we would have to place our desired frequency at in the place where there is already a lead, meaning at the higher frequency range, right? So consequently, omega c must be much larger than B, where we are going to get a lead. Otherwise, we will not be able to get a lead, because if we place it below B, that is the frequency B, we are going to get a lag from the compensator, which we do not want, would not want. Okay. So we can simplify the design by considering that the lag portion produces an attenuation of 20 log beta at omega c and a small phase phi 2. So basically what we are saying is that we are going to place our desired gain crossover frequency in the lead portion, that is at the higher frequency range. So what we would be saying is that in this higher frequency range, the lead portion is dominant. So I mean, there is a large lead which we will be getting from the lead portion, plus a small amount of phase lag which we would be getting for the lag portion. Lag portion is also there, but the lag portion will be giving us a small amount of phase lag only, say 1 degree to 5 degrees. So basically, what is done is that the lead part is designed first and designed in such a way that even if we get some small amount of phase lag from the compensator for the lag portion, it is going to ultimately keep our phase margin at the desired value. So, okay. So I will not go into the details of this, which actually follows a similar sort of, I mean, procedure to what we have already done. So the magnitude expression is given over here, and I mean, from there we get this. The phase expression, you would be seeing Q is equal to tan phi c plus phi 2. So phi 2 is actually over here. We are assuming that phi c is the amount of lead that we got from our compensator at omega c, considering that the lag portion will be giving a small amount of lag as well. So from there, now Q is substituted as this, as had been done earlier. And similarly, by, I mean, sort of numerically arranging the things and all that, we come to a similar sort of expression that is a quadratic in alpha and alpha, that is, and also Q and C, which are known quantities. So again, I mean, once the Q and C values are known or decided upon, alpha and A and beta also can be calculated. So I'm not going to go into this particular, I mean, expression. In fact, the expression I can show you, but okay, this is the quadratic in alpha that we finally arrive at. The working out has not been shown over here, but by a similar sort of methodology. A is can be computed from this expression. Calculate phi 2 is given over here. So tan of phi 2 is equal to this, and from there again another quadratic is framed. So from here we can actually find the value of B. So to sum it up, the working out and explanation I have not, I mean, given over here in too much of details. What I would be summarizing is that basically your compensator is, first of all, the frequency to be chosen is going to be lying in the high frequency range, meaning much beyond the value B. Now, if we place the desired gate crossover frequency in this portion, that is the lead portion, what we would be assuming is that we would be designing, going in for the design of the lead part only, considering that the lag part will be giving us a small amount of phase as well. So, like we did earlier, meaning that we uh, sort of preempted the fact that we will be getting a lag from the compensator and that's going to be negative. So I take a positive value so that the negative and positive cancel out, things like that. So here we are assuming that since we are going to get a small phase lag from our lag portion of the compensator, we assign some value to that, and on the basis of that, we design the lead portion. So we make our lead portion such that the lead has an additional value of phi 2 as well, so that when the lead portion is added, when the lag portion is added, that lag will automatically balance out the extra amount of lead that I have designed the thing for. So with that, that is the principle actually, and the quadratic has been shown over here. The value of A can be calculated once alpha is solved for, and then by using this expression, the value of B also can be solved for. So you recollect that A, alpha, and B were the only things that we had to solve for. And you would see that, I mean, B is calculated on the basis of the phase of the lag portion, which is phi minus phi 2. Anyway, the working out I have not shown. So by the solution of this, we can find the value of B. So with that now, just a numerical before we wind up finally. So determine the transfer function of a lag lead compensator that will provide a lead of 50 degree and an attenuation of 50 dB at 6 radians per second. So just note that over here we are asking for a positive phase, whereas a negative magnitude. That is why we are using this, right? So the procedure will be outlined. The omega c also is mentioned over here. This is a direct problem, not exactly a design problem like we did in the earlier cases. So the first thing that we have to do is we have to assume something. So we are assigning, say for example, a small amount of phase lag that we would be wanting from the lag portion. This is something that you have at liberty. You say that, okay, I want phi 2 to be equal to 2 degrees. So we had stated that it's going to be assigned between say 1 degree to 5 degree, a small amount of phase lag that we would be looking for from the lag portion of the compensator. So at omega c equal to 6 radian per second, which is a specified frequency, let us say that the lag that we would want from the lag portion is phi 2, right? So this is not going to be specified as per the problem. This is as per your decision. You would have to decide upon a small amount of value, which is, say, for example, 2 degrees over here. So from that now, we would just directly be, I think there is something is being superimposed. No? I don't know what it is. Just let me try to remove it a bit. Oh, okay. So that now, I mean, from the expressions that we had, you've already got the slides, you would be knowing. So Q is equal to tan of the phi c that we want from the lead portion of the compensator plus the 2 degree that we are going to get from the lag portion, because minus 2 degrees from the lag portion plus the additional 2 degree that we are going to consider while designing the lead portion will give us the desired value, right? So Q is calculated. C is, as I mean, given it was, I think, 15 decibels. That is what we wanted. So from there, 15 by c to the power of minus 15 by 10 is what you get. So this is c. So once c and q are obtained, put it in the quadratic, solve for the quadratic, you get the value of alpha. Once you get the value of alpha, put it in the expression for a and you get the value of a. Now once you get that, basically, next what you have to do is you have to take the quadratic for b, which was calculated on the basis of the phase of the lag portion. So that expression I told you, I have not gone into the details of the derivation over there, but you will be able to, I mean, a few steps, you would be able to get the quadratic expression. So here now, this was the quadratic, or rather, this was the quadratic, of which this coefficient is alpha minus 1 by tan of minus phi 2. So that has been calculated, and hence this has been calculated, and hence the quadratic has been framed. So once the quadratic is framed, omega c is something which is known to us, 6 radians per second as per this problem. So b can be found out. So once b is found out, and we know that alpha into beta is equal to 1, that means beta is equal to 1 by alpha. So beta you need not calculate separately. So alpha has been calculated from the quadratic, a has been found out, b has also been found out. Beta is equal to 1 by alpha. You get your compensator, right? So with that, I basically the direct design of a lag lead compensator based on some, I mean, expressions that have been derived, right? Now, as far as the design of the compensator, lag lead compensator is concerned, again, a similar process would follow. Of course, I have not done it over here. I would not be expecting you to work it out right now. But I mean, as far as the principle is concerned, again, you would have to, first of all, the steps to be followed is that, steps to be followed is that, again, you would have to, first of all, compute a frequency chart like this, frequency versus phase and magnitude, then decide on the basis of inspection of your phase versus magnitude, phase versus frequency and magnitude versus frequency, decide on where to place your omega c and on the basis of that, again, you obtain the values of MC and phi C, which you would be wanting from your compensator, and decide on the amount of lag that you would be assigning. That assignment of the amount of lag is in your hands, not dependent on anything else. It is a small amount of lag that you would be wanting, say 1 to 5 degrees of value. Once you decide on those values, you can mechanically calculate by using the expressions that have been shown to you, right? Not derived exactly, but to find the lag lead compensator given a practical system, meaning a physical system, at least the transfer function of which is given to you. Okay, so with that, I end today's class. In fact, that is the end of what I intended to cover in class. And you've just seen that after this, we have tacho generator and then AC servo motor, and I think LVDT. LVDT, I believe you've already done in your measurements, and the other portion, servo motor, DC servo motor, we've done in details. AC servo motor, just 2 or 3 pages, and basically the tacho generator principle also is described quite comprehensively, I believe. So the rest of the portion, please go through at least once, and let me know if you do require some explanation, in which case I would have to arrange for an extra class sometime. But apart from that, I would not be taking any further classes as far as this linear control system is concerned. Okay, so I will stop the recording now. First, I will be taking your attendances, but if you have any queries regarding what has been taught today or regarding anything, because we will not be normally meeting next week because your semester has come to an end. So, apart from that, if you have any queries regarding anything, you can ask me just now. Just now means while I take the attendance or after it or even before it. Let me just take your attendance before I leave you. You just respond to your roles. In case you have any queries, you can ask after that. Arnobotra, Manika Bishash, Aritro Mojumdar, Gopal Medda.
Yes, ma'am.
Gopal?
Yes, ma'am. Present.
Yes. Sharnadeep Shaha.
Yes, ma'am.